At 2:35 in the morning, Eastern Time on Wednesday, August 5th, 2026, a 4-ton cylinder of aluminum lithium alloy struck the moon at 5,400 miles per hour. It had been falling toward that moment for 19 months. Telescopes across 2 continents were pointed at the spot. 2 spacecraft in lunar orbit had been briefed on the coordinates. Professional observatories, university teams, and amateur astronomers with backyard rigs had all set alarms for the middle of the night, and almost none of them saw a thing. This is the story of what hit the moon, why nobody caught it on camera, and what the scientists who study these events are still trying to figure out. Let's begin with the object itself. On January 15, 2025, a Falcon 9 rocket lifted off from Launch Complex 39A at the Kennedy Space Center, the same pad that sent Apollo 11 to the moon. The mission had a name that would turn out to be unintentionally poetic: Ghost Riders in the Sky. It carried 2 spacecraft, both bound for the lunar surface, both built not by governments but by private companies. The first was Blue Ghost Mission 1, built by Firefly Aerospace of Cedar Park, Texas. On March 2, 2025, it touched down on the moon and became the first commercially built spacecraft in history to execute a completely successful soft landing. The second was Resilience, built by the Japanese company iSpace. It did not fare as well. On June 5, 2025, its laser rangefinder failed during descent, and it struck the surface at speed. Both of those spacecraft got where they were going because of a third piece of hardware, the one nobody was supposed to think about again. The Falcon 9's upper stage is roughly 45 feet long and about 12 feet across. Like every liquid-fueled rocket stage, it's essentially a hollow tank with an engine bolted to one end. Empty, it weighs around 4 tons. Its job that January was to fire once the vehicle had climbed out of the thick atmosphere, then fire again, pushing both landers onto a trajectory that would carry them out to the moon. Once the payloads separated, that stage had no further purpose. Normally, this is where such a stage disappears from the story. For missions to low Earth orbit, SpaceX performs a deorbit burn and the stage burns up in the atmosphere. But this was not a low Earth orbit mission. Juliana Scheiman, SpaceX's director of NASA Science and Dragon programs, explained the difference at a NASA briefing on August 3rd. For high-energy missions, she said, the company performs a different maneuver to ensure the second stage is safe under the appropriate rules and regulations. She emphasized the stage was passivated, vented of residual propellant, and drained of stored energy, exactly as the standards require. And she was direct about one thing. On a trajectory like this one, it simply is not possible to deorbit the stage. So it stayed up. It entered a highly elliptical orbit around Earth, swinging out to roughly 377,000 kilometers at its farthest point, nearly the distance to the moon itself, and dipping back in to about 9,400 kilometers at its closest. It was cataloged International Designator 2025-0010D, NORAD identification number 62719, and then it began to drift. Here's the part that matters. There's no atmosphere out there to slow anything down, but there are forces. The gravity of Earth, the gravity of the moon, the gravity of the sun, and, subtly but relentlessly, the pressure of sunlight itself, pushing on the surface of that cylinder every second of every day. Over 19 months, those forces reshaped the orbit. Scheiman described it as a mixture of solar activity and gravity forces, putting it on a path toward the moon. Independent astronomers noticed first. Bill Gray, who runs an orbit tracking operation called Project Pluto and who has spent decades doing this kind of work, was the first to publicly report in April that this thing was going to hit. NASA's Center for Near-Earth Object Studies at the Jet Propulsion Laboratory, a facility built to watch for asteroids that might threaten Earth, later ran the numbers and confirmed it. Their conclusion was not a probability. It was 100% chance of impact. Then, a team from the University of Arizona's Space Force Center and the Planetary Science Institute did something more thorough. They didn't just track the object forward, they ran its orbit backward. Using 304 observations collected by Planetary Defense Surveys between January and April of 2025, they propagated the trajectory in reverse and asked where it had come from. The answer placed the object at perigee, its closest approach to Earth, at 07/2012-05 UTC on January 15, 2025, with an uncertainty of less than half a second. When they projected the ground track back further, it lined up with Launch Complex 39A to within 59 degrees, about 66 kilometers. They had reconstructed a rocket launch from nothing but the wandering point of light it became 18 months later. Then they did something even more interesting. They took spectra, measuring the colors of sunlight reflecting off the object, in both visible and near-infrared wavelengths. That ruled out the possibility that this was a natural object, one of the small asteroids that occasionally get temporarily captured by Earth's gravity. Natural rock has a particular spectral signature. This did not. Instead, the spectrum showed absorption bands near 1, 7, and 2, 3 microns, and those bands matched a laboratory sample of white epoxy thermal control coating, spacecraft paint. It was also nearly identical to the spectrum of another Falcon 9 upper stage they observed for comparison, and in the process they stumbled onto a genuine mystery, the first of several. By measuring how the object's brightness rose and fell, the team tracked its rotation. It was tumbling with a period of about 7 minutes. But between January 10th and February 24th of this year, that period dropped by more than 8 seconds. The object sped up. That should not happen. A dead rocket in space is expected to slow down. Internal flexing, magnetic effects, and residual fuel sloshing all bleed rotational energy away over time. The paper's authors call the natural dynamics almost entirely dissipative. Something added energy instead. Their candidates? Sunlight pressure acting asymmetrically on the surface, leftover fuel outgassing from somewhere in the tank, or collision with a small piece of debris. They could not determine which. That's a spent rocket stage most people assumed was inert, doing something nobody predicted. Their impact prediction was precise. 06:33:23 UTC on August 5th, plus or minus 55 seconds, at latitude 19, 9 degrees north, longitude 265. 8 degrees between the craters Bell and Einstein, just beyond the northwestern limb on the far side. Impact speed 2, 43 kilometers per second, striking at just over 30 degrees above the local horizon. Expected crater, 40 meters or less. Other estimates varied. NASA projected a crater about 60 feet across and 12 feet deep. A separate preprint, led by Benjamin Fernando of Los Alamos National Laboratory, submitted to the Astrophysical Journal Letters, put it at 65 to 90 feet. Bill Gray calculated the impact energy at roughly 3 tons of TNT, the equivalent, as he put it, of 15,000 sticks of dynamite. The disagreement isn't sloppiness. It reflects how genuinely hard cratering is to predict. Crater size depends on the density and structure of the ground being hit, and nobody knows the local soil properties at that exact spot. So the world watched, and the world missed it. The problem was the lighting. The impact site sat on the sunlit portion of the moon. An impact flash, lasting about a second, maybe less, had to compete against the glare of a brightly illuminated lunar surface. Paul Wiegert, an astronomy professor at Western University in Ontario, described the flash as muted by the brightness of the moon itself. The site's position near the limb, at roughly where the 10 would be on a clock face, made it worse. Marco Langbroek, a Dutch satellite tracker with real expertise, had his telescope on target at the appointed moment. He got nothing. "We knew this would be a long shot," he said afterward. Across the Americas, where the geometry was best, observatory after observatory came up empty. Not one direct image of the collision exists. And yet we know it happened, because of one telescope in Chile. The European Southern Observatory's Very Large Telescope at Paranal was watching, using an instrument called the ultraviolet and visual Echelle spectrograph. Rather than trying to photograph a flash, that team was looking for chemistry. And they found it. Barbara Ferreira of ESO confirmed the telescope detected spectral lines of sodium and lithium gas in the impact plume, lasting 5 to 10 minutes. Carl Schmidt of Boston University, who led the observations, said the gas cloud extended a few tens of kilometers into space. He told the Associated Press he is 100% certain his team's observations revealed signs of the crash. Read that result carefully because it is elegant. The sodium came from the lunar soil. Material blasted off the moon and vaporized. The lithium almost certainly came from the rocket, whose aluminum-lithium alloy tanks were vaporized on contact. 2 elements in the same plume, one from the target and one from the projectile, appearing together at the predicted time and place. Nobody photographed the crash, but a telescope 4,000 miles away tasted it. Jonathan McDowell, the retired astrophysicist and probably the most careful cataloger of orbital objects alive, put it plainly to the AP. "There's no doubt in my mind," he said, "that the rocket is now in teeny little pieces scattered over the moon near Einstein crater. As a physicist," he added, "I know that what goes up must come down. There is a coda worth mentioning." Within hours of the impact, fake images and videos claiming to show the collision were circulating on social media. If you see dramatic footage of this event, treat it with suspicion. The real evidence is a spectral line on a graph. What remains unresolved is substantial. We still don't know the true crater size or shape. We don't know how far the ejecta traveled. Wiegert's estimate is that rock could have been thrown as far as 500 miles before falling back. We don't know why the object spun up, and we don't have a single picture of the scar. That last one is being addressed. NASA's Lunar Reconnaissance Orbiter circling the moon since 2009 passed over the site on July 29th and was scheduled to return on August 12th. Comparing those 2 passes should reveal a fresh crater where none existed before. Brent Gary, LRO's project scientist, said the team can do additional targeting about a week after the impact. South Korea's Danuri orbiter, carrying the ShadowCam instrument, is also attempting observations, though the Korean Space Agency said its imagery will only be released once analysis is complete. There's a precedent for what comes next. In 2022, a rocket stage hit the moon near Hertzsprung crater. When LRO photographed the site, it found not one crater, but two overlapping ones. An eastern pit, 59 feet across, a western one, 52.5 feet. Nobody had predicted a double crater. Scientists concluded the object must have carried significant mass at both ends, unlike a typical spent stage where the mass concentrates at the engine. That object was later identified through the same combination of astrodynamics and spectroscopy as the upper stage from China's Chang'e 5T1 mission, launched in 2014. So the honest summary is this: a 4-ton piece of human hardware, launched to help 2 private spacecraft reach the moon, spent 19 months being nudged by sunlight and gravity until it fell. It hit exactly where and when the mathematics said it would, and the only reason we can prove it is a faint signature of sodium and lithium recorded by a telescope in the Atacama Desert. The photographs are still coming. When they arrive, we may find out that this crater, like the last one, doesn't look like what anyone expected.